This is part 2 of chapter 25 homework preview. So in this video I'm going to go over number 33, 29 and 18 from chapter 25. Let's start with number 33. The setup here looks something like this. You've got two charges, and in the question you're actually given values for both the charges and their position on the x-axis. I'm going to leave it general. The important part is that it's symmetric, right? The same charge, same magnitude of charge, one positive, one negative, and they're at opposite coordinates, right? So this is at plus some value, this is at minus some value from the origin. The first question asks us, is there a point anywhere along the x-axis where the electric field is 0? Right? So is the E field, part A, is the E field 0 anywhere? Now, of course, the electric field is going to be 0 at infinity, right? Because you're infinitely far away, and the electric field falls off as 1 over r squared. So if I plug in infinity into 1 over r squared, I get 0 for the electric field, no matter how big the charges are. Even if it were just one charge. The fact that there are opposite charges, so that the net charge is 0, actually means that the electric field falls off faster than 1 over r squared as you go further away, because the distance between them becomes less and less significant the more I zoom out, but that is beside the point here. The question is the electric field 0 anywhere other than at infinity? Right, so definitely infinitely far this way, electric field is 0. Infinitely far this way, electric field is 0. That makes sense. But anywhere else? Well, let's plot the electric field. Well, the electric field starts from positive charges, goes into negative charges, right? This is a dipole. You know what it looks like. It's sort of these sort of arc shapes like this. I'm just going to plot it along the x-axis. Plot the electric field lines here. It'll look like this. One comes out here, goes in there. Over here, the electric field comes out, and here it goes in like this. Now, could it be that this isn't quite right, and that the electric field due to this one cancels out the electric field due to this one somewhere over here, say? Could be, right? Well, not in this case. Right, so let me say this again. This one creates an electric field that goes outwards in all directions, right? So if it were just for this charge, there would be an electric field to the left over here. This one, however, is going to create an electric field to the right, somewhere over here. Is there ever a place where the two cancel out? No, there is not. Because they're the same magnitude of charge, but if you're on this side, you're always closer to this one than to this one, which means this one's always going to win. So the electric field over here is always going to be to the right, because the contribution to the field due to this charge is always bigger than the contribution to the field over here due to this charge. Similarly, if you're over here, is there a point where the contribution from those two cancels out, right? The plus wants to create an electric field to the right, the minus wants to create an electric field to the left, if you're somewhere out here. But because of the same magnitude of charge, and if you're on the right, you're always closer to the plus, that means the plus is always going to win. They're never going to cancel out. And if you're anywhere in the middle, well, then the fields actually add up, right? Because if you were a little positive charge, you'd get attracted to the minus, repelled by the plus. It's like they work together. The answer is no. Electric field is 0 nowhere except at infinity. Now, what about the potential? That is part B. Is the potential equal to 0 anywhere? Again, it is going to be 0 at infinity. Now, in this case, I actually think it's easier to answer B and C together. Now, C asks us to plot a graph of the electric field strength and of the potential as a function of x, as we go along the x-axis. So let me do that. So B and C. So I'm going to draw the x-axis here, and there's 0 here. There's my point D here. This is where the plus charge lives. Let's put it there. And there's the x equals minus D over here. This is where the negative charge lives. So what are the potentials? So potentials add. Right? If I've got two charges, they each sort of create their own contribution to the overall electric potential. So let me work one by one. The negative, if I have the negative charge alone, the negative charge essentially creates a deep sort of pit if I plot the potential. So negative charge, I guess let me draw it like this. So I'm going to draw an axis here. There is going to be the axis in which I draw the potential energy. Let's see if I can make this drawing work. I'm first going to draw the potential energy just due to the negative charge. And that is going to look something like this. It's always negative. And it does something. This should be symmetric, by the way. This is very poorly drawn, clearly. Those two sides should look the same. I'll try to do better next time. So the expression, right, is V due to the minus is going to be KQ over R. So Q in this case, though, it's a negative minus Q. So minus Q over R. So it's like a 1 over R. In this case, R is X. Oops, I should have. Let me just write R for now. R minus, meaning the distance from the negative charge, that is minus KQ. The distance from the negative charge is given by x, your x value plus D. You can check that it is true, right? If I'm at 0, x equals 0, my distance is D. If I'm at x equals minus D, my distance is 0. If I'm at x equals minus 2D, then my distance would be minus D. So that works out. Now, if I just want to plot the potential for the positive charge, let's see if I can do a better job here. It looks the same, except that the charge is positive, so the whole thing is positive, but it still falls off at 1 over R. So it looks something like this. And then it shouldn't go up, right? This goes to 0 at infinity, right? The potential due to the positive charge is going to be KQ, in this case plus Q, over the distance from the positive charge. Let me write it like this, which I could write as KQ over X minus D. Absolute value, right? The distance from this point here is given by the X value minus the value of the point here. But crucially, it falls off as 1 over distance, so it does the same shape. It goes to infinity as you get closer and closer, right? If you right at a point, you'd have to divide by 0. It doesn't really make sense, but as you get closer and closer, the potential gets bigger and bigger. In this case, in the positive direction. So then the total potential is just the two of them added up. And by the symmetry, and again I've drawn this very poorly, especially I think this line here. We draw this one like this. Pretend this isn't here. Right? By the symmetry of it, this one and this one are going to cancel out right in the middle. So if I add those two functions up, the green one and the blue one, that's going to give me the total potential. Let me use a new sheet to make this somewhat less messy, right? So I'm going to add those two functions. Let me redraw those axes. This is my potential energy. This is my x-axis. This is d. This is minus d, so this is where the negative charge lives. This is where the positive charge lives. If I combine the two, right, I'm literally adding those two functions together. Imagine I'm taking this plus this, but I'm going to do it graphically. Well, if one of them goes to infinity, but this one's finite, it's still going to be infinity, right? This thing here plus this thing here is pretty much this thing here. Similarly, over here, if I add a teensy bit of positive potential to infinite negative potential, it's still infinite negative. So the potential we're going to get is going to look something like this. And then it goes to 0. Not here, it keeps going to infinity and only reaches 0 when you add infinity. But what it does imply is that the potential is 0 right there. Right? What is not 0 is the slope of the potential, and the slope of the potential determines the electric field. So the electric field is going to be, in this case, to the left, and it's going to be, the strength of it is proportional to the slope of the potential graph. Right? So E field, the magnitude of the E field is equal to the magnitude of the this is not potential energy, excuse me, this is just the potential. Same thing up here. I hope you caught this. This is just potential. It's confusing, right? Watch the concept overview video, but I agree it's terrible terminology that, why did people not come up with better ways to distinguish the two? So the electric field, though, is the slope of the potential. Direction is down the hill. So if I plot the slope of this, you can't see this, but I hope you've got it in your notes now, so that you can look at it while I'm drawing this. This is your x-axis. I'm now going to draw the x component of the electric field. So I'm not just drawing the absolute value, I'm actually drawing it, in the positive or negative, because I understand that if I have a positive charge in one place, negative charge here, positive here, then the electric field along this x-axis is just always in the x direction, positive or negative. Just by the symmetry of the setup. It's never off to the side. So if I draw the x component of the field along the x-axis, I actually draw the strength of the field and also the direction. So in between it's going to be negative. Over here it's positive. Over here it's positive, right? Electric field to the right in the positive x direction. Electric field to the left, negative x direction. Electric field to the right in the positive x direction. Now if I draw this, and so here is the point, here's minus d, here's plus d. The electric field I'm going to get, right, it's negative between those two, positive on the left and right, and if I look at the slope, right, the slope, it's not just this goes to infinity, it also becomes infinitely steep. Same thing here. Infinitely steep to the right, infinitely steep going to the left. So my electric field is actually going to look something like this. The x component of my electric field. And this should be symmetric. I'm awful at drawing these curves, right? It should be symmetric hill, with this being the highest point. And then it looks something like this, where this is essentially an asymptote. So this shouldn't become vertical, it just becomes steeper and steeper and steeper. Now you could do that, you could actually check that that makes sense by working out the slope of this function, right? So you plug in the function, and remember this is just v total is v plus v minus, like we've defined it before. And you can differentiate that with respect to x to figure out what the slope is. And you then should be able to find that this slope does indeed give you this curve, and if you're feeling extra ambitious, you can check that this is the maximum, a local maximum right here at x equals 0. But so because this electric field is negative throughout the middle, right, the force on a positive charge would always be to the left. That makes sense, away from positive towards negative. If you're on the right, the positive charge wants to move to the right with the direction of the electric field, and the closer you are to the positive charge that's already there, the stronger the force. Yes, makes sense. Opposite thing over here. If you're a positive charge, it gets added to the system. Really close to negative charge, with a strong force to the right. If you're further away, it's going to be very weak. So hopefully drawing it like that makes sense to you. Alright, let's go on to the next problem. So the next question is number 29. It's actually a really easy one. It's mostly just plugging in values, but there is an interesting little tangent that I want to explore a little bit. So the first part asks us to find the potential due to the proton at the position of the electron. Right? So that means we're ignoring the electron, we're just asking what is the potential right here due to this charge here. Right, so this is kind of how people imagined an atom would look, a hydrogen atom in this case. Of course, we know that that is not really accurate. It is not literally a little moon going around a sort of planet proton type of thing. Right? We'd have to use the laws of quantum mechanics to actually describe this accurately. But let's right now, we're going to run with this model. So we want to calculate what's the potential here. So, we just use the equation for the potential of a point charge. So you plug this in, you know that the charge of a proton is just a thing we call E, confusingly, right? While the charge of an electron is minus E. But, you look up what those are, you plug it in. And then the potential energy of the system is, well, what's the potential here? That would be the potential energy if 1 coulomb was placed there. Instead we place an electron there, so we multiply the potential by the charge of an electron. U is often used for potential energy, while V is used for the potential. Again, confusing, I know, this is something to get used to, it's a convention. That is E times V. Looks like the unit electron volt, it's not, right? This is the electron charge, that is the same thing, but by V here, I mean the potential. And this is another confusion, right? V as the unit of volts versus V, the symbol to represent the potential at a point. Again, context hopefully makes it clear. In print, you'd see this one be sort of written in italics, whereas the unit, not shown on this page, would be not in italics. Just try to always understand what it is that you're doing, what your symbols mean. But you just plug this in, and you get the answer. Now, here's something I want to show you about this kind of setup, and of something going in a circle, right, due to an attractive force. And I'm going to do it with the proton and the electron, or an electrostatic interaction, but you could do exactly the same thing with a gravitational interaction, right, where instead of a electrostatic force, you've got a gravitational force, say, the moon going around the Earth. I want to show you something that is called the virial theorem. And this is going to be a very cute little theorem about potential energy and how it relates to kinetic energy. So, little aside, it's not going to take us very long, so please bear with me. Actually, only a special case of the virial theorem, which in full is more general, applies to all sorts of other interactions. So, the potential energy of a system like the one above, right? So you have it on your paper, hopefully. U is equal to K Q1 first charge times the second charge divided by the distance between them. In our case, that is K times the proton charge times the electron charge, which is minus E, so I'm going to put a minus in front, E times minus E divided by R. But you might as well work with the general case. It doesn't matter. Okay, now what you know is that the force, right, is a centripetal force. So electrostatic force has the role of a centripetal force. It keeps something going in a circle. The electrostatic force is given by K Q1 Q2 over R squared, and that's equal to, well, the centripetal acceleration is V squared over R, so we multiply it by the mass ma, right, to get mv squared over r, the expression for general centripetal force, where m is the mass of the thing going in the circle. So in our case, that would be k e squared over r squared is the mass of the electron times v squared over r, with this being the speed of the electron. It doesn't matter though, right? Electrons or protons or just some two other oppositely charged particles, it doesn't actually matter. Okay, we've got those expressions. Now, if I look at this one here, or let's go with this one here, let me write it down again. Right? So we had, let me just write it down again. Q1, Q2 over R squared is mv squared over R. Right? This is telling me the electrostatic force acts as a centripetal force. It keeps something going in a circle, but the thing going in a circle is moving with speed v divided by the radius. It's moving with speed v, we squared it, divided by the radius, times m. That is the centripetal force. Right? So that is something you know from Phys 161, except we've got a different type of force that you didn't know about before, right? But it doesn't change the right-hand side. The right-hand side you understand from 161. So let's simplify this. Right, I can cancel the r, one of the r's, with this r here. So I get that k q1 q2 over r is equal to mv squared. Now if we look back, k q1 q2 over r is the potential energy. Right? This is just the potential energy. What's the right-hand side? mv squared. Where have we met that? It's the kinetic energy. Well, kinetic energy is a half, so this is just twice kinetic energy. So what this shows you is that the potential energy, if something goes in a circle, due to a 1 over r square force law, if something goes in a circle due to a 1 over r square force law, you're going to get that the potential energy is twice the kinetic energy. Now actually, I lost the minus sign here. There should be a minus sign here, right? Because it has to be like an attractive force with a minus sign. But that's beside the point, right? this relationship stands. And this is what's called the virial theorem. It means, let's say, up to sign. Interesting, right? Try the same thing for gravity. The q's don't actually matter. All that matters is the 1 over r squared dependence of the force law. So, curious little fact here, but that's it for problem 25.29 and a little aside along the way. 25.18 concerns a proton beam, so please make sure you read the question carefully before you watch the rest of this video, otherwise it won't make much sense. So the idea is you've got a beam of protons and you shoot them by essentially accelerating them through a potential difference. So it's like you put them on the top of a hill, except it's not a literal hill, that it's a high electrostatic voltage, high electrostatic potential, and you let them roll down, figuratively speaking, this potential hill to a lower potential, so they lose potential energy, they gain kinetic energy. And it tells us that they move from a potential that is some value to a potential that is 10,000 kilovolts lower. That's what we mean when we say they get accelerated through a potential difference of 10,000 kilovolts. It's saying they start on a hill that is essentially 10,000 kilovolts high. And they roll down and they speed up in the process. Notice this is kilovolts, right? So there's a factor of 1,000 hidden in there, in addition to the 10,000 that's already there. So what that allows us to do is it allows us to find the potential energy per proton. Right? U for one proton is going to be the proton charge multiplied by the potential difference. It's called delta V, right? That is just this thing here. Right? The analogy is, imagine I've got a hill, and the hill is a certain height. That is my delta V. If I put something there, it has a certain amount of potential energy. Well, to get down to here, it's going to speed up by a certain amount that's determined by delta V. There's a subtle difference here in that if you've got a gravitational force, the mass is actually going to cancel out, so any object is going to have the same speed when it gets down there, which doesn't happen in electrostatic interactions because you've got the potential energy is determined by the charge, but the kinetic energy is determined by the mass. But that is a subtle difference I want you to think about more in your own time. Okay, so we've got this potential difference. We're rolling this down the hill, and so we get a certain amount of potential energy, so a certain amount of kinetic energy per proton. Right? We know we want 0.1 joules, or whatever your value is, total. We know the potential energy that's got turned into kinetic energy for each proton. So how many protons to make 0.1 joules? How many times, you can't see this, how many times do we need delta V times the proton charge to make 0.1 joules or whatever value it is that you have in your question? And that will solve you the problem. Well, that gives you the number of protons. You're asked to then find the total charge, but you know how to do that, right? We have the total number of protons So, you know, you can find the total charge from there. Now, if you've paid attention, you might be able to see that there's a shortcut here. I could have just figured out what charge do I need to multiply by delta V to get the desired energy. It's a little shortcut here. But again, if you understand this method, then you might understand the shortcut. I don't want to do the shortcut right away because I think it would be more confusing and helpful. Okay, so that concludes the second part of this homework preview. In the last part, I'm going to preview numbers 46 and numbers 57.